Okay, let's have a class, and we will talk about the water again, and we continue to talk about this water. Number 2, first of all, we want to mention is we call it so-called sorption isotherm. Okay. Now, what means isotherm? That means at a fixed temperature to see the sorption situation of a food product. Now, here is the first thing we want to mention. I have a food product, let's say. This is a food product. And we will have some moisture goes here. So they're going to absorb. They will absorb the moisture. Now, in the whole system, let's say in the environment, there is some of the moisture going to go out. So we call this sorption. Now, at the end of the day, this will reach a balance, which means our food products in the environment will be in a movable balance for their absorption and desorption of the moisture. This is where we call it equilibrium moisture content. So acronym we call it EMC. Once it's reached the balance. Okay, now in the older time, people are going to do some of the research. How do they do it? They have a closed chamber. This is a closed chamber, let's say. In the closed chamber, they put a tray. There is a tray there. Inside of the tray, they're going to put a water. And with different salt solution. Now, this salt solution could be sodium chloride or calcium chloride or others, because when they add salt, the moisture content of the environment will be different. You know that, and it's related to relatively humidity content. So they put some salts there. And what they do, they put a holder. This is a holder. And they put our food products right on the top. This is the foods. Okay, then what they do, they will do a measurement of the water activity and also the moisture environments of the food products. And then they're going to get a curve. What's the curve going to look like? We mentioned that before, we're going to re-mention. The curve is y-axis is EMC, equilibrium moisture content. And the x-axis is relatively humidity, or we call it water activity. Okay, if it's relatively humidity, also we call it equilibrium humidity. It will be from 0 to 100%. If it's water activity, it will be 0 to 1.000. And you know that the REH is calculated by AW multiplied by 100%. Now, what's going to be the curve looks like? We mentioned earlier, the curve going to be looks like for most of the food products. It will be like that. It is S-shape for absorption. Okay, so it goes this way. That's we call absorption of moisture for food products. Now, how about desorption? Do you think it will be just go back? No, it's not exactly go back. How do you do? They shifted the left side a little bit. So it looks like this. Then goes here. That curve, we call it desorption. So shift to the left a little bit. Now sometimes some of the food products, this area is the same, almost over flat. And remember, we manually separate these into 3 locations and 3 sections. Section number 1, number 2, and number 3, which is mono layer. Most of them are bound water. And this is we call it additional layer. And the last one we call it free water or capillary water. And I tell you one thing for our food products. The mono layer and the additional layer, there is about 5% only. And the 95% of the moisture content is capillary or free water. Okay? So here is the curve. Now we want to mention several things. Number 1, this curve, the absorption and desorption of the moisture for food products is not simply reversible. Therefore, we give them a terminology called hysteresis. It's not simply reversible. Now, we want it simply reversible, is that right? If any products can do simply reversible for absorption and desorption of the moisture, then will be a good thing. Because the food safety will never be an issue. If you have a beef, let's say this is a beef. Okay, I absorb to water. Then I desorb to water. It's completely reversible. Then I don't have to worry about that. When I don't need to eat it, I take out all the water out. When I want to cook it, I put all the water back. Because when the water is out, there is no moisture, there's no water activity, the bacteria will not grow or very unlikely to grow. So food safety will never be a problem. But unfortunately, there is a phenomenon called hysteresis happens. Okay? This is the first thing I want to mention. Now the second thing I want to mention, this is a standard curve for S shape for most of the food products. Some of the food products will looks like is a L shape, not an S shape. Well, this is still EMC, and this is water activity, or equilibrium, relative equilibrium humidity. What do these products look like? This is usually we have a high sugar content in the food products. And you will see they are very sensitive to the environmental moisture, which means they are very sensitive to how many water moisture around it in this closed chamber. Okay? And we also can see on the very top here, the capillary area, there's a very limited amount of the water absorption there. So just want to let you know, some of the food products is L-shaped, but the majority of them are S-shaped. Okay? Now, why we need to talk about this? What we care about absorption? Because we want to see some of the foods may be called hygroscopic, which means they are very sensitive to the environmental moisture contents. Now, why we care about desorption curve? Because we care about whether the drying process, how the drying process is gonna work. Okay? So this is the second thing I want to mention. Number 3, how we understanding the hysteresis? Why it is not exactly reversible? There is a lot of theory to talk about that. And this curve comes out about like 90s, 40s, 90s, 50s. Lots of the theory, lots of the experiments conducted to explain it. But the best one to explain and the most simple one to understandable is in our textbook, which is an ink bottle model. This is the one pointed out by Dr. Labuza, Tender Labuza, around 1960s. Now, Dr. Tender Labuza is still there. He's a great American chemist, a professor in University of Minnesota Twin City. And he is a PhD, obtained his PhD degree of food chemistry at MIT in 1960s. He was the last batch of the students graduated from MIT, got a PhD degree of food chemistry. Later on, MIT, the food science program is cut. So he's very talented and still very active. I saw him a couple of times in the conference, although I never talked to him. He pointed out this ink bottle model. So what that means? Okay, let's say we have a ink bottle, something like this. Okay? We have a second one like this. Please think about the theory is when we do the absorption of the water is filling here, is that right? Come in. We will more care about is this radius of the bottom, so the R at the bottom. Because if we want to fill it, we need to, let's say we're going to fill the water. It depends on how fast we're going to reach the middle, how fast we can cover the R radius. But how about disruption? Disruption we are more care about is this neck, the small R. Because when the water is all here, it depended on how the water is going to go out. It depends on how the size of this small R. Because he thinks the theory is that the absorption, disruption, they pay much attention at the capillary area. And the capillary area looks like an ink bottle. So it's very easy to understand why it's different, because when we feel it, we're going to see the size of the bottom. But when we do the disruption, it really cares about the size of the neck. So that's why it's not reversible. Okay? So this is something I want to mention. Now, last one I want to mention here is, in the history, there is a several equation named by different people, different authors, will explain the kinetics. Basically, is the monolayer volume when we talk about absorption of the water. So I want to introduce to you one by one. Then back in 1912, there is the first formula equation comes out. It's called Langmuir equation. Okay, what is that? What it looks like? This is what we talk about is A minus. The theory is A divided by V equals K divided by B Vm added by A Vm. What are they? This Vm is monolayer volume. What is A? Water activity, we know that. Okay, what is K? 1 divided by P0. What is P0? That is the vapor pressure of pure water at a fixed temperature. Now be careful, when we talk about the fixed temperature here, we are referring to is Kelvin. I'm not sure you learned in the physics class. It's not degrees Celsius, degree Fahrenheit, it's Kelvin. That's international standards. Now what is the B means? This is a constant. So based on this Langmuir, M-U-R-I, based on this Langmuir equation, we could calculate it as a monolayer volume. Now how we do that? This is their standard curve. Okay, it comes out like that. A, x-axis. Y-axis is A and V. So what's the curve going to be looks like? Like this. What's the slope? So slope equals, how about here? That is K B V M. This is called the intercept. So we can calculate the Vm value. Why we can calculate the Vm value is so important, because we can know the surface absorption area. This is calculated by Vm divided by m, the molecular weight of a water, this is 18, multiplied by 60.2, multiplied by 10 to the 23, this is Avogadro constant. And the last one will be A0, that is the water surface area. So we can do the estimation of the S0. However, later on, people find this Langmuir equation is not really fit for the surface. Why? Because for the surface, this B, although it's a constant, but it's no longer a constant. The reason is the Langmuir equation originally coming from gas and some of the solids. Now for the surface is different. If based on the Langmuir equation, what happened will be, they will be to do the absorption in fixed sites. And they're going to do is one by one. But in reality, for the surface, when they absorption the water, it's not going to be one by one. They're going to be do most of them at the same time. So this might not be a very good idea to talk about the water surface. Okay, then which one is a good idea? So we're going to talk about second equation. The second equation is called the BET equation. Okay, what is the BET equation talks about? This is by three authors, B. Brunner, B-N-E-U-R, E. Emmett, T. Taylor. So Brunner, Emmett, and Taylor have this equation. What's going to be this equation looks like? A divided by 1 minus A V equals 1 divided by Vm modular C at A C minus 1 and VMC. Now what is C? This is a heater constant of a fixed material, okay, of a material. of absorbed material. You can move that a little bit there. Good. Thank you.
Mm-hmm.
Just cover the surface, make sure you can see.
Yep.
Okay? So, when we have this one comes out, the same thing as the Langmuir equation, what's the equation going to be looks like? What's the curve looks like? X-axis is still AW, water activity. So y-axis is A, 1 minus A, and V. So what's going to be the curve looks like? The curve going to be looks like this. What's going to be the interslope? The slope is equals, will be C minus 1 C Vm. How about the intercept? This will be 1 divided by VMC. That's going to be the intercept. Then we can calculate the Vm. Now, we're not going to go to the detail of the calculation. All these things, there is a software right now, we can do the calculation. Like we are doing the bacterial growth curve, the same thing. But I want to introduce these to you. And this type of the curve, you also need to know, is a little bit different, difficult understanding. It's like your Michaelis constant of the enzyme. It is a relationship curve, the formula. It's not like when you learn in the physics. Did you learn PV equals nRT? Did you learn VT equals V0 and is that like this? These are straightforward formula. You know, it's different. These kind of a relationship formula and the relationship equation, you need a curve and you need a figure to do the calculation. Now again, we're going to calculate is a Vm value because of monolayer value. People think it's important. Okay, so let's have the camera go that side a little bit.
Okay.
I want to talk about here. So both of these, Langmuir and the BET equation, we all talk about is what? Is a monolayer value, is that right? Basically, is this area. So, there is a limitation for that. The BET equation basically is fit for foods has water activity is around 0.1 to 0.5. Because when the food, the water activity is fit this area, most of them is in the first part, is in the monolayer, is the most important section of their moisture contact. Okay, so there's a limitation for this one. Now, then the question is, why people think the BET equation is going to be better than Langmuir equation? Because this is allow multiple sites absorption at the same time. Not like Langmuir, you have to do is one by one. So that's why people think this is the advanced curve and the advanced one. However, later on, people find BET equation is only for the food products about water activity 0.1 to 0.5, but how about the other ones? Therefore, there's another equation comes out in 1981 called the Gab equation. So what is Gab equation? Guggenheim, Anderson, and the Bohr equation. Okay, that the equation what it looks like. I still can remember it. You may learn in your physics a little bit, which is kind of in here is W K C M A W, and then this is going to be 1 minus K A W and multiply by 1 minus KAW, and then add CKMAW. And all these three, which is a constant of absorption material. And this comes out 1981. This one we call it a general formula or general equation. This fits for the foods at water activity equals 0.0 to 0.9. And there is a modified one, which is an advanced Gab equation, can fit all the foods. And where are they? And I put a textbook, which is a paper, which is on the eCampus. Can you just adjust the?
Oh, yeah.
Adjust a little bit. On the eCampus, then you can see it. Okay, you can read about that. So until here, there is a three equation. In the history, they talk about the monolayer and the sorption isotherms of the water products in the foods. Okay, so it is a little bit complicated, it's not that easy. Now, why people care about that? Because we need to know what kind of the packaging material we need. The reason is we care about the quality of the foods and the shelf life. Is there going to be an enzymatic reaction happens? Is there going to have a mild reaction? Is there going to have a bacteria growing there and a pathogen growing there? That's why people developed all these equations and also have a related software for that. Okay, so this is something I want to mention in our first section. We talk about is sorption, desorption, isotherms. Okay, so this we're going to be stopped from here. Then we will talk about is the ice. Please move the camera a little bit on the side. Then we're going to talk about the
Like
ice.
this way?
Yeah, just cover this area.
Oh, okay.
You can look at that to make sure it's all covered with rice.
Yeah, it is.
Okay. So we finished talking about the water. Now we want to talk about the ice. The second section. There's a lot of the stuff we can talk about the ice. So first of all, what is the structure of the ice? This is water molecule surrounded by, connected with other 4 water molecules. And we mentioned it before, is by hydrogen bonds. In tetrahedral arrangement and form a hexagonal halo structure. Because of this, so the density of the ice is equal to 0.9 gram per ml. So compared to the water, it's a little bit slow, it's a little bit small. That's why the ice can float it on the water surface. This is, you know about that. Now, what the hexagonal halo structure looks like? If we want to draw, it's very simple. I don't draw a cubic one, okay? Just draw a flat. It looks like this. Then how about the hydrogen bonds? There is always like this. One is inside, one is outside. So one is inside, another one is outside. One is outside, another one is inside. One outside, one inside. And one outside, another one is inside. All like this. Now, if you want to draw a little bit cubic, one like that, like here, so like here, like here. At this angle, 109. Same as method, okay? This is what it looks like. So we want to talk a little bit more. If you want to talk a little bit more, we can talk. Every hydrogen, there is a two side kind of connected to oxygen. Is this side or the other side? So we can say, if there is an M molecule, water molecule, theoretically, how many arrangements of the hydrogen atoms surrounded with oxygen atoms is 4n. That's theoretical. However, we have a restriction because every hydrogen atoms has to be surrounded by two oxygen atoms. So you based on the mass, realistically, there is a 1.5 times n different arrangement of the hydrogen atoms. Okay? So that is our basic knowledge. Now, we don't care about all these things too much right now. We will maybe talk a little bit. We mainly talk about is the freezing. That's going to be the key because it's for the chemistry class. We care about is the freezings. Okay, so what are we going to be? First of all, you need to know the 0 degrees Celsius. We are talking about is a pure water. 0 degrees Celsius is the freezing temperature of water. Now, when we say this is a pure water, 0 degrees Celsius is also the melting temperature of ice. This ice is also composed by pure water. This is the first thing you need to know. This is number one. Okay, number two. If we add a salt solution there, what's going to happen? In a real food products, it barely has pure water situation. They all have salts, sugar, carbohydrates. What's going to happen?
It's gonna melt.
Yeah, the freezing and the melting temperature will be decreased. You know that. We had a blizzard, we have a snow, is that right? How we want to melt it out soon? Spray a salt. Now make sure that salt is usually not sodium chloride, it's calcium chloride, because calcium has 2, is that right? Charged by 2. Now why we add a salt, the freezing melting temperature will be decreased. Now there is two basic theories about that. Number one, remember this structure? This is the easiest one to explain. When you add a salt, this salt's going to break down here. So the salt will be break down. The hexagonal halo structure, which means it's favor the freezing, favor the melting. And the other side is favor the freezing. This is the first one. They're going to break when you add a salt. Because these are hydrogen bonds and it's very weak. So you add a salt. It's like dissolved there. It's ionic bond is also weak, so they interact with each other. This is the first theory. The second theory, which is in your textbook, which is mentioned. So let's say this is a water molecule. It is there. When the water molecules they become ice, they like purity. They don't like impurity. If you have ice, if you have a salt there, what's they gonna do? They'll try to repel it. They try to push it away. So therefore, they're gonna have different layer comes out. They push it away, push it away, push it away. So the salt goes out. Is that right? Then they're gonna form a different crystal. This is the crystal, right there. Okay, then what happened? In this area, there's the ingredients. There is a gradually decreased concentration of the salt. But they still have water there. And those water are super cold. Super cold. So maybe here is 0 degrees Celsius, that may be minus 10, and at the end of the day, it will be reach equilibrium status, then the temperature might be 0.5. So that's another theory, which means you have a salt there. When they have the crystal, they're going to repel because they want the purity. And then surrounding those crystals, the ice, the water is supercoiled. Because you know what means 0 degrees Celsius. I always ask students in the lab, you have ice, you have a water. The mixture is 0 degrees Celsius. Here, which means you have ice, you have a salt, and you have a water. That mixture is lower than that. That's why the temperature is low. So there is a two theory we can explain about that. Okay, so this is the basic knowledge. Now the second thing we want, now the key thing here, we want to talk about is this crystal. And followed by the nucleation. Okay, so what's the story? This is going to be the key for the food products. This is number one. This is going to be this is number one. This is number two. Okay, so what that means? We have a water molecule right here. This is a water molecule. We draw a couple. This water molecule, if at room temperature 25 degrees Celsius, they are actually moving. You know that because of hydrogen bonds, and they are vibrating. Okay, when the temperature decreased, let's say decreased to 5 degrees Celsius, they started to moving slow, and then they started to become sluggish. It's like our human being, we become sluggish when we shake and when we feeling cold. Then the temperature continues to cool down to 0 degrees Celsius. What's going to happen? They continue to do sluggish. Then they do aggregation. Which means these water molecules are going to be all aggregated together. Then become an embryo. Become an embryo. This embryo, if let's say the temperature goes to -5, -10 degrees Celsius, temporary, okay? Then you heat it back, then maybe disappeared. If this embryo continue existing, they will become a nucleation, which means they will become a nucleus. Now, when they become a nuclear, they also going to be happen is a crystal. Will become a crystal. Now, how they become a crystal? They need to be reached a critical. How they do a nucleation? What we say, a critical size of an embryo. Now, what is going to be the curve of the critical size? It looks like this. This will be a critical size of nucleus. And this is the temperature, let's say. Let's say this is the temperature. Okay, let's say 0. This is go to -30. This will be 30 nanometer, 60 nanometer, and maybe 120 nanometer. What's the curve looks like? The curve looks like this. So what happened? If a food products or a pure water products, let's say a pure water, you cool down it just below 0 degrees Celsius. Their critical size of the nucleation is very large, like this. Okay, so what that means, the crystal will be very large. If we cool down the temperature, goes to -30, that will be very small. Is that right? It's a critical size. Here is the key. if you have a small number of nuclei, which means large size of crystal. If you have a large number of nuclei, which means you have a small size of crystal. The crystal, we don't like it to be too large because it will damage the tissue. Think about you have a beef products. You do frozen in your home refrigerator up top. Is that the freezer? You freezing about a month or 2 months is okay. You take it out. If you're freezing about 6 months, you take it out. It's horrible. It's not going to be tasted very well because the tissue has been damaged. If you have egg mayonnaise or margarine or those type of the products, you frozen too long, the emulsified fatty acids will be separated because of the crystal. So we don't like the crystal. What's going to happen? What are we going to do? You have to do is decrease the temperature real quick. That's called supercooling. So you decrease the temperature very, very quick from 0 to minus 30. Then the critical size of the nucleation will be dramatically decreased, maybe only like 10 nanometer. You can have a nuclear. So the crystal size will be very small. So instead of you have a big chunk, you're going to have a small size. Now, of course, there is a lot of theory behind that. They say the location of the nuclear size, the size of the crystal is important. The location of the crystal is important. On the surface, in the middle, and at the end, it may be different. However, the key is you have to do a supercooling. And the research has been showing if you supercoil from 0 degrees Celsius to minus 40 degrees Celsius, the probability of nucleation is 100%. In other words, even you put your beef to the top of your home refrigerator in the freezer, which is about minus 20, minus 10 degrees Celsius, more or less there's still some free water there. Okay, although you see it's tough, the water has still available to be used. Now the thing I want to mention is this type of the nucleation, when we're using a model so far, we talk about is the water, is that right? This is called homogeneous nucleation. So I'll just take this off. Therefore, the nucleation has 2 types. Number 1 is homogeneous nucleation. This is basically is pure water. But I tell you, it's barely happening in food products. Number 2, more often happened in a food is heterogeneous nucleation. This is basically happens in all kinds of food products. Okay? Now, here is the question. We don't like the crystal. We want the crystal is the smaller the better. So what the industries they do? There is several things they can do. Okay, number 1. They are adding the ingredients inside. We call it the seeding. And that's an example of heterogeneous nucleation. And I can give you 2 examples right on in our textbook. A fine ground lactose into evaporated milk in the evaporator. This is the first thing they do. At this moment, these lactose added, they want the water there to form nucleation, so the crystal size can be as small as possible. Number two, they are adding crystallized small fatty acids into a heat exchanger in manufacturing margarine. This one we will talk about all the time. Shortening and the margarine we will talk about all the time when we mention the lipids. Because these small fatty acids is also like acidic. Okay? The third method is what they do. This is called protective freezing. A common example is liquid nitrogen. What is the boiling temperature or melting temperature or freezing or let's say the freezing temperature of the liquid nitrogen? Is minus 196 degrees Celsius. So there is a food product, let's say. I'm going to add in or put in a liquid nitrogen container. When you add it, what's going to happen? It's going to boring, is that right? The liquid nitrogen will be boring. Then the vapor layer will be surrounding these food products. This is, you don't have to worry about anything inside the crystal. We don't form the crystal. We will be just have a vapor, very cooled, super cooled vapor.